Hi everyone, so this is where we are going to start or pick up from. We are still on chapter 7, so now we're going to get more into the structure of the atom, where the electrons are, how we can calculate that change in energy as it is either jumping up to a higher energy level or falling down energy levels. Okay, so we're going to talk about what is called the Bohr model. So if you guys remember Niels Bohr, he was the person who added on the concept of energy levels in the structure of the atom. So we still keep that concept that we do have these energy levels, and but he stated that these electrons are kind of orbiting around the nucleus, going around in a circle, but they don't, okay? But we do keep his concept of energy levels. All right, so what we are going to do is we're going to take a look at his model in this equation. So this equation here is for an electron in a hydrogen atom. So we discovered that this equation will only work for hydrogen. It doesn't work for any other atoms. So this equation will be used to calculate energy transitions of an electron in hydrogen. Okay? All right, so the equation here, energy equals negative 2.178 times 10 to the negative 18 joules. All right? The z squared here represents the nuclear charge. So hydrogen has a nuclear charge of 1, right? It has 1 proton. The N in this chapter represents energy levels. All right, so this will be the energy level that it is transitioning to and from. Okay, so that's N squared, right? N, once again, represents the energy level. So since this equation only works for hydrogen, so then the Z will just be 1. Okay, and so 1 squared is equal just to 1. So then sometimes what you'll see is, you'll see many times that this equation doesn't have z squared written in it, because since it's going to equal 1, then we don't really need to say z squared because it only works for hydrogen. This equation is not on the pink sheet. You don't have to have it memorized. I will write it on the board for you for the test. All right, so also according to Bohr's model, and as we get into energy levels and stuff, this is just a term that we are reviewing. So remember, the ground state is the lowest possible energy state for that atom. So in other words, that is where the energy level is equal to 1, okay? When n equals 1, that is the lowest possible energy level. Okay, so if we wanted to calculate the change in energy for the hydrogen, we're going to calculate the energy of the final state minus the energy of the initial state. So remember, anytime we're calculating change, it's final minus initial. All right? So this is just an equation to help you remember that we're going to take in consideration the wavelength and parts of the wave. Okay, and how that is all associated with energy. So we will do some sample problems in class involving these equations and calculating the change in energy. All right, so now what we're going to do is we're going to take a look at all the different orbitals, all the different sublevels, and what these sublevels look like. These are, remember, electron clouds. So this first one, as you can see, these are s orbitals. Okay, so notice this is a 1s, which means in the first energy level, second energy level, third energy level. Notice as you add on energy levels, it gets bigger and bigger in size. Okay, so this is showing you the energy levels around the nucleus, okay, for each energy level. So remember, electrons are found in these electron cloud regions about 90% of the time, okay? 10% of the time, they're like in between the energy levels, all right? So this is what an s orbital looks like. This is what your p orbitals look like. So remember, there are 3 different p's, okay? 3 different p's. We have one along the x, one along the y, and one along the Z. Okay? Remember, these are the P's, so P represents what we call a peanut-shaped electron cloud. All right? So there's 3 different P's. So remember, how many electrons can we fit into each orbital? 2. So there's 2 electrons bouncing around in this cloud region. 2 electrons bouncing around in that cloud region, and 2 electrons bouncing around in that cloud region. Okay? So that's why we say the P's have 3 different orientations in space, and you can fit 2 electrons into each one. And this is what your d orbitals look like. So you can see the majority of them look like 4-leaf clovers, okay? Except for this last one, it kind of looks like 2 pacifiers stuck together. These little pictures are like scatter plots of the electrons, okay? The electrons that are moving around in those orbitals. So you can see that's how they got the shapes of the electron clouds, okay? So the d orbitals have 5 different orientations in space. 1, 2, 3, 4, 5, okay? 5 different orbitals, and then once again, how many electrons can we fit into each orbital? We can fit 2 electrons, right, into each orbital. So once again, 2 electrons bouncing around in there, 2 bouncing around there, so on and so on. All right, this is what the f orbitals look like. You count them. Remember, there are 7 f's. 1, 2, 3, 4, 5, 6, 7. So the ones that are down here look like flowers. So since since flowers start with the letter F, that's how you can remember that these electron clouds look like flowers, all right? So 7 different orbitals, and then once again, how many electrons can fit into each one? 2, right? So 2 electrons into each orbital. So remember, there's a pattern, okay? S, P, D, and F. There's 1, 3, 5, 7, and then 2 electrons into each one. All right, so this is a review of electron configurations. All right, so you can take a look. Remember, the S's are filled in the first 2 columns there. Remember, your only exception is row 1 because there's only 2 elements in row 1. Your P's are in this region, the D's are there, and the F's are at the bottom. So if you look at period 4, right, so you go 4s, but remember, the transition metals are 1 energy level behind, and then once you're done with transition metals, then it goes back to 4, okay? So that is something that you should remember and pay attention to. And then if you look at rows 6 and 7, okay, those 2 rows there are really inserted here in row 6 and 7, right? But the F's are 2 energy levels behind. So it's like it would go here and then go down here. Once that's done, then it goes back up to the D's like that. All right? So we will practice doing electron configurations in class. Now remember, your electrons, when they are in an orbital, they have what we call opposite spin. Okay? Your electrons must have opposite spin. All right? So you can see here, 1 is spinning up, 1 is spinning down. Okay, they're spinning in opposite directions, and that is to keep the atom more stable. Okay, keeps the atom more stable. All right, now the off-ball principle states that anytime we are writing an electron configuration, we always have to start from the beginning, okay? So we always start at the top of the periodic table, and we run our finger across the periodic table until we get to that specific atom. All right, Hunds Rule. So Hunds Rule states that we have to have at least 1 electron on each line before we can pair it with the opposite spin, okay? So for an example, if you find a nitrogen on your periodic table and you write out the electron configuration for nitrogen, 1s2, 2s2, 2p3. And then if we wanted to write out the orbital notation for that, remember each line represents an orbital, okay? Remember, there's only 1 type of S, so that's why for the S's, I only drew 1 line. There are 3 different P's, that's why I drew 3 lines for a P. Okay, so if we wanted to fill in the orbital notation for nitrogen, we use arrows to represent the electrons. So one is spinning up, one is spinning down, because this is 1s2, so then I put 2 electrons in the 1s. There's also 2 electrons in the 2s, so I'm going to fill those electrons, one up, and one down. Okay. Then we get to the next one, 2p3. All right, so that means I have to put 3 electrons in the 2p's. So according to Hunds Rule, I have to have at least 1 electron on each line before I can pair it. So notice I did 1 on each line, and I did not do this. 1, 2, 3, okay? This would be incorrect, all right? And it's incorrect because I cannot pair this one yet until I had at least 1 electron on each line. Now, once these are all filled, such as shown here, these are all already 1 on each line, right? Then if it was 2p4, then I would go back and now pair it. So that would be 2p4, then that would be 2p5, and then that would be 2p6. Okay, so that is how you would fill the orbitals. You should know what the term valence electrons mean. All right, so remember, valence means the electrons in the outermost energy level. So the electrons in the outermost says principal quantum level, which is energy level. All right, so all you have to do is, remember, the shortcut is look at the group number. The group number will tell you the number of valence electrons in that outermost ring. So if you find calcium on your periodic table, you should notice that calcium is in group 2, therefore it has 2 valence electrons. Nitrogen is in group 5, therefore it has 5 valence electrons. Bromine is in group 7, that's why it has 7 valence electrons. So this is just terminology that you should be familiar with. You should also understand the term inner electrons. So when we're talking about the inner electrons are the electrons on the inner rings, okay? Or the electrons in the inner energy levels, not on the outside. So another term for inner electrons, we call them core or kernel electrons, okay? These are the ones on the inside, not the outside. And then you should know some categories on the periodic table based on their electron configurations. So there is this term called representative elements, okay? We also call these the main group elements. So this is where the S and P orbitals are, we usually say, partially filled, okay? So in other words, like groups 1 through 7, okay? Groups 1 through 7. So that's where you start to fill the S and Ps. Some periodic tables also will consider your noble gases as part of this representative group, all right? So you can say groups 1 through 7, or you can just say groups 1 through 8, and then both of those would be fine, all right? So you can see some examples that are listed here. The reason why we call those representative is because we have a combination of metals, nonmetals, metalloids. We have all different kinds of elements, and so they represent a wide variety of chemical and physical properties. All right, your transition metals, you should know where those are located in the middle section of your periodic table, and then what we call the lanthanide and actinide series, which are also called rare earth metals. Those are the 2 rows at the bottom of the periodic table, or what we also call intertransition metals. Once again, that's where we start to fill the Fs, right? 4F and 5F gets filled down there. So you just need to know where these groups are located on your periodic table, okay? The last thing I want to go over are these 2 terms, okay? Whether we consider the spins or the electrons to be diamagnetic or paramagnetic, all right? It has to do with whether or not the electrons are paired or if the electrons are unpaired in the orbitals. So once again, if we take a look at the nitrogen that we did, remember it was 1s2, 2s2, 2p3, right? So if you look at the orbital filling, right, the 1s's were filled, the 2s's were filled, and then for the p's, they were half filled. 1, 2, 3. Okay? So then a question would be, how many electrons are diamagnetic and how many electrons are paramagnetic? Okay? So di, if you remember, right, di means 2, so then that will help you remember that means paired. Now take a look at your nitrogen, right? So let's take a look at the nitrogen. So how many are diamagnetic, okay? In other words, how many are paired, all right? How many orbitals are paired? So then you have this one that's paired and this one that's paired, okay? So you would say it contains 2 orbitals that are diamagnetic. And then how many orbitals are paramagnetic, unpaired? So unpaired would be 1, 2, 3. 3 of them are unpaired. Okay, so just make sure you are familiar with those terms. All right, so that is everything that I want to talk about today. And then we will do more practice of electron configurations and using Bohr's equation in class. All right, I will see you later. Bye.